Okay, 12.5, sigma notation. Let's get right into that. So whenever we want to express a sum and not have to write out every single stinking term in a series, especially when you're talking, getting in the upper teens and 20s and 30s in terms of numbers of elements in a series, you're going to want to shorten that up again. Like I've said many times before, mathematicians are lazy. They want to be able to write with the least amount of stuff possible. That's why they invented sigma notation, which always indicates a sum or a particular series. And let's just go through just the anatomy of sigma notation. So when you look at this here, a sub n is just merely your expression for your general term. When you have that n equals 1 down there, it could be n, could be any variable, it doesn't really matter. That's just a starting value, so they want you to start by plugging in a 1 into the general rule. And then that value that's placed up at the top is the maximum value for your sequence. And we call that n there, called the index of summation. So let's see it in action. So let's look at a problem like example A over here. So just to go through this process again, a sub n, the general rule there, it's n squared minus 3. They want us to start our series off by plugging in a 1 and do every term after that until you get to 4. So us plugging in a 1 right in here, we have 1 squared, which is 1, 1 minus 3, we end up with negative 2. Now because this is sigma, they want us to do a series, so we have to add each successive term. So plus, now we plug in a 2 in there, 2 squared, that's 4, 4 minus 3 gives us a 1. Go on to 3, 3 squared is 9, 9 minus 3 is 6. And then plug in a 4 there, 16, 16 minus 3 is 13. When we add all those up, we end up with a final score of 18.
Cool tricks! Cool tricks!
Reminder, if you want to use the graphing calculator here, hit the alpha button, then hit window. You're going to want to pick this guy right there, number 2 there for sigma notation. Understand that they give you this preset parentheses here, so anything that they give you here, let's try that again, anything that they give you in here, you have to put the entire thing in there. You enter and it spits out that answer for you. Cool trick, cool trick. Alright, let's look at the other example. A couple things to note what makes this one different. Notice now we're dealing with a geometric series. Also notice that this is an infinite geometric series. Now notice what I was doing here with my graphing calculator. There's no way you can actually do infinity in your calculator, so a nice little trick there would be to make it go to a ridiculously high amount. I'm not going to advertise that you take it to 10,000. I did that. I was sitting there for a while. Maybe 100 ought to do it. Remember, it doesn't take a whole lot of iterations here for that fraction of negative 2/7 to go straight to being practically 0. So you don't need a big number there. Notice what else needed to happen here in order for this to work properly. When you go through summation notation and sigma notation through your graphing calculator, what they give you are those preset parentheses right there. So notice when I was typing this thing in here, I was very careful to keep the x minus 1. Notice that looks like it's out of parentheses right there, but really it's really only out of these parentheses here. But still keep it sandwiched in between the first parentheses they give you. Everything needs to go inside those two parentheses. So there we have our answer of 3.8 repeating. Now going in the other direction, if you were to look at a series and be able to express it in sigma notation, this is now, it's game time here from when I was giving you guys all that practice in 12.4, being able to write the general rule. This is why I was having you practice that in 12.4, so that way you can do stuff like this, is be able to deal with these series that are neither arithmetic or geometric. So when you look at these here, try and figure out just some sort of trick that's going on here. And we looked at a couple of tricks that are most commonly thrown tricks at you. This one here uses perfect squares, but kind of uses it in a little bit of different pattern. Do you recognize that pattern? Notice that each term is 1 less than a perfect square. Notice that the first term it's 16 minus 1. Second term 25 minus 1. 36 minus 1. 49 minus 1. All the way up to 144 minus 1. So what we can get out of that is this general rule right here of n squared minus 1. Now, since that 4 squared minus 1 would be 15, and then 12 squared minus 1 would be 143, what we've just nailed down here are those two values that we're going to use as our interval when we're using our sigma notation. Notice we're using those going from 4 to 12. Now, one thing that you noticed here is that we didn't start off with 1. Well, the cool thing about sigma notation is you don't necessarily have to start off with 1. And a lot of times it actually makes writing the rule a lot easier if you don't start with 1. I mean, we talked about this, or we're going to talk about this. How would that model change if you forced yourself to be 1? Well, you'd no longer be going to 12. You'd have to go out to 9. And then having n squared minus 1 won't really cut it to get that first term. We'd have to get a little bit more clever with it and do n plus 3 squared, because 1 plus 3 would give you 4, so then you square the 4, and then you subtract 1 from there. So notice sometimes going with 1 isn't always the most efficient way to get your general rule. So let's take a look at these two. If we look at the one, look at example A, 5, 10, 15, 20, 25, notice that series is arithmetic. So we could start maybe using our cheat sheet if we need to. So a lot of you might be saying, oh, well, that's easy, it's 5n. Once again, not all students see it as quickly as others. So what I found is the best way to go about doing this universal and everyone can get onto this rung of the ladder, the low rung here, is let's just start with the general rule that we got pretty good at earlier in the unit. And then let's just plug in the information that we know. The first term was 5. And our common difference there is 5. So I need to put in 5 for a sub 1 and put in a 5 for d. Now we just turn it over to algebra and let algebra take over with this problem. Distributive property right there. Then notice the 5 and the minus 5 can cancel out. So now we're left with 5n here. So now you can put that 5n right up there. And then when we go through the rest of this here, what do we need to start? To start off with our first term being equal to 5 up there. Yeah, we got to start off with 1, and then we got to go to 5 to finish this thing off. The other one's really, really annoying. I mean, certainly it's not arithmetic, it's not geometric, and it's really not easy to figure out the rule here. 2 to 4 to 10 to 28, yikes. One other one that we saw there is we were taking numbers and squaring them each time earlier. Maybe this one might be cubing it or something like that. Or maybe we can start with 3 and raise it to some bases there. I think that's it. Take a look at that rule. If we take 3, raise it to a power, and then add 1 to it, we can end up with those. However, adding 1 to it is contingent on us starting with our n values being 0. And if we have that being 0, we have to go 0, 1, 2, 3. So notice we finish off this series by saying that we're going from 0 to 3. And you'll run across some other ones here. You notice what the trick is with this one is notice that the signs alternate. So when those signs alternate, there's a pretty slick and underhanded way to kind of generate the alternating in signs, and that is the fact that when you take a negative number, raise it to an even power, it turns positive. You take a negative number, raise it to an odd degree, it turns negative, right? So we can kind of use that knowledge to our advantage here because we're going to be going and increasing by integer values for our terms. So, nice little trick here. Does it qualify as a cool trick? I don't know. Some of you might not think it's that cool. I think it's kind of cool. So a kind of cool trick. For sequences that alternate signs, if that first term, like in this situation here, is positive, then we could use this right here as a nice little sneaky way of generating alternating signs. However, you're kind of forced to make that initial value be an odd number. So we're kind of forced to make this start off with 1. And if we make this thing go to 1, because we have a total of 5 terms in there, we can make this thing stop at 5. Now, looking at the rest of this here, once again, I kind of highlighted this and illustrated my pattern for finding general rules here in 12.4 video. And that was, look at all the fractions as a whole, and you can clearly see it's not arithmetic, and you can also clearly see it's not geometric. So then you just focus on the numerator. Another thing that we can get away with doing here, because we've already dealt with the alternating sign, is that you can just focus on the absolute value of these numbers, 2, 4, 6, 8. You don't have to worry about 2, negative 4, positive 6, negative. Don't worry about that. 2, 4, 6, and 8, and 10. That's just an arithmetic sequence in which all the numbers are increasing by 2. So we'll just tack on this little rule on top of it. Notice that we started off with n being 1, so that'll give us all those terms right where in the right spots. Look at the denominator though. Denominator 2, 6, 24, 120, and 720. Not recognizable pattern. However, if you looked up here, that was kind of floating up here this whole time was factorial. Notice that 2 factorial is 2, and 3 factorial is 6, and so on and so forth. So really what we're looking at up there, down below in the denominator, is a factorial situation. However, if we made this thing just be n factorial, we'd have to plug in a 1 there, and 1 factorial is 1. So what we need to do is modify n factorial and say, well, start off with n being 1, but then add 1 to it for each term. So that way you're starting with 2 and then going to 3, 4, and 5, and so on. Actually, 4 and 5, and then you stop right there, right? So there would be our general rule. Now, in fraction form. So let's try and put it all together here. First thing I like to do when I'm dealing with, say, number 36 right there is, not every one of these things are written as a fraction. If they take the time and make a couple of them fractions and not make the other ones fractions, go ahead and make them all look like fractions, and that might get the ball rolling there a little bit. And once again, we need to write a general rule here. Notice that 5 isn't going anywhere anytime soon. Also notice that we got just dot and dot and a dot and then nothing afterwards. So that means that this thing is an infinite series. So notice that 5 isn't going anywhere. So we'll keep that 5 right there. Now notice the bottom. Do you notice that right there when you have the 2, the 6, and the 24? You can go back one further there. That's 1 factorial, then 2 factorial, 3 factorial, 4 factorial. Why are there 2 1s there? Well, it's that little rule right there, that little bylaw there in that definition of n factorial. By definition, 0 factorial is also 1. So notice that this little the series here kind of forces our hand in terms of what number to start with down there, which is good. I mean, we kind of like it when the problem kind of forces us to go in one direction, not take us multiple different directions. You know, and n has to be 0. And then we can write just simply n factorial down below and we're good to go. Now look at the mess over there for number 40. Once again, it'd probably be a good idea to focus on just strictly the numerators, get that rule, and then go down to the denominators and write those. If you look at just the numerators, something a bit squirrely about the 3, the 8, and the 15. I think we saw this before, didn't we? So right back here with this example, when every single one of those terms was 1 less than a perfect square. I think we have the same thing here. Yeah, 3 is 4 minus 1, 8 is 9 minus 1, another perfect square, and then 15 is 16 minus 1. So how can we write that? I suppose we can just say that this is a perfect square, so n squared. Take a number, square it, and that's 1 less, so minus 1. Now think about what that forces us to make here for our first value. Also notice the dot 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 right there, so that's got to be another infinite series. And then if we really want to make this n squared minus 1 like this, 1 perfect square less, don't we have to start with n being a 2? Yeah, we have no choice here. Let's just hope it works out for the denominator as well. Now, something else is kind of squirrely about this denominator. I'm not sure why this particular example would go through the process of only and not multiplying the 9 times the 2 and the 27 times the 6 and the 81 times 24 without having you maybe have something of importance to stare at when you just look at the first factors and then the second factors. You know, I think they want us to look at each one of those separately. So when we go to that denominator there, if we're looking at just the numbers in green, hey, that's pretty easy to spot. 9, 27, 81, that's taking a value of 3 and raising it to the nth power. Now good news here, you take that 2 that we first started off with and plug it right in there. 3 squared is 9, 3 to the third is 27, so we don't need to worry about changing that initial value there. Just think about this, if we had to change the initial value, then that would definitely change the rule that we had in the numerator too. So this is where these problems could get a little bit annoying if you are struggling with knowing where to start for your initial value. Now what about those purple numbers up there, your 2, your 6, your 24? Boy, where have we seen that before? How about right back here? So once again, that's another factorial situation right there. So let's just start with that and see if we can roll with that. If we start with n factorial here, plug in the 2. We get 2, check. Plug in the next one would be 3, 3 factorial, that's 6, and then 4 factorial. So I think we got it. And I think we had this one, right? Except for that check mark right there. That check mark's not very mathematical, is it? So let's get rid of that. Okay, so there we go, sigma notation.